Ever wondered how clicking a link in your web browser actually tells your physical network card to go out and fetch a web page? I mean, it feels instant, but under the hood, there's this really powerful, deliberate divide inside your operating system. Today, we're going to dive into that divide, the two separate worlds of kernel space and user space, and why this separation is the absolute key to everything your computer does.
So, what's the big deal? Why not just have one big program run everything? Why go to all the trouble of building this wall in the first place? Well, as you're about to see, this separation is the secret sauce that lets modern operating systems be both incredibly stable and secure.
So here they are, our two worlds. On one side, you've got kernel space. Think of it like the inner sanctum of a castle. It has the highest level of privilege possible, what's sometimes called ring zero, which gives it direct, totally unrestricted access to all the hardware, the CPU, the memory, the disks, the whole shebang. And then on the other side is user space. This is a protected, walled-off area where all your applications live. They have zero direct hardware access. For anything they need, they have to go and make a formal request to the kernel.
Now, this whole setup is no accident. It's a very deliberate design choice, and it's based on one incredibly powerful idea, the principle of least privilege. It's simple, really. Your photo editor has absolutely no business reconfiguring your CPU. By giving programs only the permissions they absolutely need to function, the system builds a protective wall around its critical core, shielding it from bugs or even malicious code. Just think about it. If your browser crashes, you just close the app. But if the kernel crashes, the entire computer goes down.
And you don't have to take my word for it. This quote, right from the kernel's own documentation, just says it all. The kernel is built with the assumption that everything coming from user space is potentially hostile. It's this guilty until proven innocent mindset that explains exactly why that separation is so strict and so vital for a secure system.
Okay, so if these two worlds are so carefully walled off from each other, how does anything actually get done, right? How does your word processor actually save a file to the disk? Well, the system has built some very specific, very secure bridges to let them talk.
They talk in three main ways. First up, you've got system calls. Think of these as the official front door. An app uses a system call to formally ask the kernel for a service, like, hey, please open this file for me. Second, there are pseudo file systems. These are kind of like special virtual files that act as a window, letting us peek into what the kernel is doing. And finally, there are very controlled debug interfaces, which let developers and their tools safely inspect the kernel.
Let's dig into those pseudo file systems for a second, because they're pretty cool. If you've ever poked around the folders on your computer, you might have seen these. Proc has information about every single thing that's running. In fact, after a kernel panic, this is exactly how tools can go in and perform an autopsy to see what went wrong. Sys gives you a way to view and even control your hardware. And debugfs, well, that's a powerful playground for developers, giving them all sorts of low-level controls.
And this brings us to what might be the most important point of all. This separation, this wall, it's not a limitation, it's an enabler. By protecting the kernel, we've created a space where we can build a massive, incredible ecosystem of powerful user space tools to manage, debug, and even extend the whole system.
So let's start with something we all rely on every single day, the tools that manage our data. Every single utility that we use to create, check, and repair the file systems that store our precious files, all of them live and run safely in user space. For instance, there are tools like mkfs.f2fs to format a drive specifically for a flash device, like in your phone, or xfs_scrub, which can perform live health checks on a running file system without taking it offline. Even super advanced tools like thincheck, which has to verify these really complex storage setups, they all run as normal user applications, just talking to the kernel through those safe bridges we mentioned.
Okay, managing files is one thing, but now let's get into the really mind-blowing stuff. The incredibly sophisticated tools that developers can run from user space to find the trickiest, deepest bugs hiding inside the kernel itself.
You see, the kernel has these amazing built-in bug detectors, but it's the tools in user space that actually give us a window to see what they found. KASAN is a master at finding memory errors. KCSAN is like a detective that hunts for these super subtle data race bugs. And kmemleak is brilliant at finding memory that was used once but then never given back. All of these are controlled and monitored from user space, usually using that debugfs interface.
All right, this next idea is one of my favorites. How do you test if your system can handle things going wrong? Well, you make things go wrong on purpose. It's a technique called fault injection, and it's an incredibly powerful way to build more resilient software.
And you do it all from Userspace. With just a simple command, you can write to a file in debugfs and literally tell the kernel, hey, next time an app asks for some memory, just pretend you don't have any. Or you can say, pretend the disk just had a major I/O error. This lets developers test all their complex error-handling code without having to, find a physically broken hard drive. It's so clever. And finally, our third big category here is all about innovation. This architecture allows for incredible new features to be added directly to the kernel, but in a way where they are completely managed and controlled from the safety of Userspace. And there is no better example of this than BPF. Seriously, this technology is a total game changer. It lets you run these tiny, safe, sandbox programs inside the kernel itself to do all sorts of amazing things. So, how do you load them, inspect them, and manage them? With a Userspace tool, of course. A tool called BPF tool acts as the command center for this whole powerful system. So let's zoom back out and really put a bow on this. This whole separation between the kernel and Userspace, it's not just some nerdy, abstract detail. It is a foundational design principle that has massive, real-world benefits. And this quote from the kernel docs just nails it. By moving complicated things, like a device driver, out of the kernel and into Userspace, you get these huge advantages. You can write it in almost any programming language you want. You can debug it with standard tools, and most importantly, if it crashes, it just crashes the driver. It won't take the entire machine down in a kernel panic.
And that's really what it boils down to. You get safety because a bug won't cause a catastrophic failure. You get flexibility because developers can use modern languages and libraries they're already comfortable with. You get debugability using all the standard tools. And you get speed. Not necessarily raw performance, but the speed of development. You can update a Userspace driver without ever having to reboot the whole system.
This idea is so important that we even have entire frameworks built just to support it. The Userspace I/O framework, or UIO, is a perfect example. Its whole purpose is to make it easier for developers to write hardware drivers that live entirely in Userspace, letting them skip all the complexity of working deep inside the kernel.
All right, so let's wrap this up. What are the big things to remember? First, that kernel and Userspace split is the absolute bedrock of a stable and secure operating system. Second, it's what makes this massive ecosystem of tools for management and debugging possible. And third, it creates a safe playground for incredible innovation, letting us extend the kernel's power from the outside in.
And that leaves us with a really fascinating question to chew on. With all these powerful frameworks for drivers, for extensions, even for virtual devices all running in Userspace, that world is getting more and more capable every day. So what does that mean for the future of the kernel itself? Is it going to keep shrinking, becoming an even smaller, more minimalist core, as more and more logic gets pushed out to the vibrant and safe world of Userspace? Now that is a trend worth watching.